Hi, Jeff Disher here again. Today I'm going to talk about graphs and trees as basic abstractions over certain ways of looking at problems, transitions, and data sets. This will be sort of a precursor to a later talk we'll do, or set of talks that go into more depth into specific kinds of algorithms we use which are based on these to try and solve certain kinds of problems. But this is a basic primer. So first of all, what is a graph? Well, a graph is just an abstract connection between points. So you can have a bunch of what's called vertices, which are just the points. They could be locations on a map, they could be states in like a process of some sort, and then there's the edges between them, the connections, and that describes how you move from one vertex to another. That could be like a rail link between two cities. It could be the logical path you take to change from one mode one state in a program to another. So that's basically what these are. So the simplest way you can think of this, and one of the things that it's used for a lot, is actually describing state transitions. So you can have a program that's got various states. Some it's doing processing, some it's waiting for the network, some it's waiting for the user to make a decision. And there's sort of the connection between how it moves between each of these states can be considered a graph. When you see people doing something like standing at a whiteboard trying to map out what they're going to build in a computer, that's usually the kind of thing they're doing. There's other kinds of graphs they build in that situation too, but that's one of them. So in terms of the graph itself and how it's actually being put together, there's a bunch of things to keep in mind. The graph itself can either be directed or undirected, or non-directed. The directed kind are ones where the connection between 2 points can only be traversed in one direction. So like a program, it can go from some state of running to like some stopped state, and it doesn't go back, or to some crash state. It can't go back. That's not how it works. So that's why you'd have a directed relationship, not a non-directed relationship. Also, there's the notion of weight. An edge can have a weight, which is just a number or a cost or a value associated with it. So to take that path, to take that edge that connects two vertices, that's the weight of doing so. You can have graphs where the connections in both directions don't have the same weight, which is common if you're thinking of the weight of, say, the air travel connecting multiple cities. Well, rarely can you go from one city to another and then back and have it take the same amount of time both directions. Usually because of things like jet stream and other sort of atmospheric factors, that's not the case. And so we use things like weights to describe that. So the example that I have for this, that's sort of a very, very easy high-level view, is connections along a train track. So, for example, this rail connection, which is common for people like me in the past, is in southern Ontario. There's rails that connect between Ottawa, Toronto, Kitchener, and Hamilton, but they all do so via Toronto. So this is a very simple example of you can't go straight from Ottawa to Kitchener. There's no direct path there. You always go through Toronto. But this graph it's bidirectional. You can actually go either way on any connection. So it's not like you go to Hamilton and get trapped there or something. No, you can always go back and forth. So it's a very, very simple example of what this means and how it works. And this is generally how people would draw a simple graph like that when they're trying to map out an idea. Something which is related is what's called a tree. So a tree is just a special case of a graph. All it means is that there's no cycles in it. So a graph can, for example, have the way of moving in a circle between multiple states. Trees don't allow that. Also, you can have a collection of disjoint trees, which is called a forest. A simple example of this is, I was trying to think of a good one that's in terms of a non-technical concept, the most obvious one being a tree. It has a root, and it has branches, and it has leaves. The leaf never connects back into a branch or anything like that. You're always moving in one direction, further out from the root, which is actually called a root in these concepts, through the branches to the leaves. Those are actually the terms that we use when describing trees as a data structure themselves. A file system is a simple one as well. So it is something which is technical, exists in a computer, but it does actually map directly to what this means. So you have everything in the Unix system starts at /. That's the root. In fact, it's literally called the root when we refer to it technically. You could have under that a directory called home and one called etc, which has logs in it, and the home has various user accounts and documents and things like that. This is a tree. That's how file systems are structured. And there's this kind of simplification and this way of thinking about the connections makes it very easy to say certain things. For example, you can always look at how much space is used by the entire home directory, all the things underneath that, because you know that since there's no cycles, you're just going to have to walk through each of the files and directories and count them all. That's easy. If it were a graph where you could go in circles there, any algorithm that was just trying to do something that simple would get stuck. They'd have to do something more complicated to remember where they were, where they'd already been, that is. So trees are useful for these very, very simple concepts. So there's some other specific uses in terms of what we do with them within computers. And I'll go into some of these things in more detail in a future talk, because they get quite involved, and they're much more along the lines of some of the algorithm studies for things like the sorting algorithms I've done in the past. But this is just supposed to be a high-level view to touch on what these things mean. So one of the very obvious examples that we have in trees is for things like searching. A binary search tree is the easiest example of that. You always have a node which has a left child and a right child and a value. So you could have, usually what this does is, you'll have an entire tree that's all different numbers that you're adding into it. And as you add a number, it tries to find out where it's supposed to go in the tree. You start at the root, follow all the way down, taking either the left child, if the left child is going to be the numbers that are less than the node, the right child is the one that's greater than the node, so you always know that there's this implicit sorted order. Traversing a tree is very quick, because you know that you're only going, on average, log n, or log base 2, of the number of entries you have. Now, there's problems of how to keep the trees balanced, because they can degenerate into linear scans, and that's something I'll go into in a future talk, but the basics are, you just walk down the tree like that, and you can find things in it pretty quickly as well, because adding and removing both do the same thing. They both walk down the tree, starting with the root, and they're always saying, okay, am I greater than or less than this node? If I'm less than, okay, I'll go to the left child. If I'm greater than, I'll go to the right child. And they very quickly cut down a lot of the decisions or pieces of data that I have to look at. It's also part of why it's used for things like file systems. Object graphs are a more sort of generalized way of looking at larger problems and connections between data. So you'll have like the components of a program, for example, that your web browser can talk to, the network can talk to the operating system, the browser can also talk to what's going to draw things in the screen. There's all kinds of connections like that. I know in the past, when I was working on the JVM at IBM, that was one of the things we talked about all the time, is the graph of the objects in the user program that was running on the VM. How are those connected, and what can we say about them? How can we optimize that arrangement? So this is the kind of thing that comes up a lot. So I'll get into these in greater detail, doing things like talking about search trees and balance trees and certain more complex types of trees, but also some things like graph solving algorithms and ways that you find the shortest path between 2 points in a graph. There's something called Dijkstra's algorithm, which is common there. Because these things come up a lot, and they're of interest to people who are just starting to get into computer science, because there's usually a lot of study on these areas, because they are very important and relatively constrained and simple. But there's a lot you can get into with them. That's a very interesting way of thinking about problems. So anyway, if there's any comments or questions, post them here or fire me off an email and I'll get back to you. Thanks. Bye.